So we know that buffers resist change in their pH. We know that they are a combination, and anytime you have a buffer, it is going to be a combination of a weak acid plus its conjugate base, or a weak base plus its conjugate acid. We know we have an equation for our buffers. If our x is small with respect to the initial, and trust me, it's pretty much going to be, that our pH is going to equal pKa plus the log, base 10 log, of the concentration of the base over the acid, and these are the initial values. Now what we're going to do is we go through here, we are going to add strong acids and strong bases to the buffers, and we're going to need a new type of chart. We are going to need a Mol chart. So give us a minute and we're going to get there. So let's start and make sure we can do buffers. So we have a solution, 1 liter, volume is going to become relevant in a moment, that contains 0.15 molar of ammonia and 0.35 molar of ammonium chloride. What is the pH of the solution? Well, first of all, we have a weak base and we have its conjugate acid, which means we have a buffer. And if we have a buffer, we know that pH is equal to pKa plus the log, the base over the acid. Now, you're going to look at this and go, but this is a weak base, not a weak acid, and that's true. And we can look our values up, and we can find that Kb for our ammonia is equal to 1.76 times 10 to the minus 5. And because we have Kb, we know we can get Ka for ammonia. We know that for any acid-base conjugate system, we know that Ka times Kb is equal to Kw. So if we do the math here, we're going to get Ka for ammonium is equal to 5.68 times 10 to the minus 10. Right, Ka times Kb is Kw. So if we can do that, we can plug this in. We're going to get that pH for our buffer is going to equal to minus base 10 log of 5.68 times 10 to the minus 10 plus the log of the base. And all we have to do is go up here and identify which one is the base. It's ammonia. We're going to put in 0.15 divided by the concentration of the acid, which is 0.35. When we do our pKa here, we're going to get pKa is equal to 9.25. When we do the log of the base over the acid and we combine these, we're going to get our total pH of this is equal to 8.88. It is going to be a little less than the pH of the pure mixture if these guys were 1 to 1, because we have more of the conjugate acid than we have of the weak base. So now we got to think, because now we have to verify that this thing is a buffer, that it actually resists change in its pH. So we are going to add something, and we're going to add a strong base. So we got to know what we have. We have in our solution ammonia, and we know that ammonia is a weak base, and we have ammonium chloride, and we know what to do with salts. We know we take our ammonium chloride, break it into ammonia and chloride, and then ignore the chloride. So if we're going to add a constant solution of hydroxide, we know that hydroxide, or sodium hydroxide, is a combination of Na plus and OH minus, and we're going to ignore the sodium. And we're going to look at this and realize that this is a weak base, this is a weak acid, and this is a strong base. Now, this is going to react. Our strong base is going to react with our weak acid. And when it does this, we're going to get OH minus reacts with NH4 plus. We have to rethink our arrows because this is strong, it's one arrow. It is going to go entirely into ammonia and water. Now we need a new chart. Because we have one arrow rather than two, this is not an ice chart. We're going to call this a mole chart. And with our moles, we have to remember that volume times molarity is moles with the units of volume in liters. So if you do not have a 1 liter solution, you are really going to have to stop and think about how much you have. We're going to have an ICF, where F stands for final. Why? Because it's not molarity. We're going to start out with 0.1 moles of this. Now we can leave it like that because we've been told moles and not molarity. In order to get moles of ammonium, we have to take our volume, 1 liter, multiply it by the molarity, 0.35 molar, and we're going to get 0.35 moles. So that's a mole, that's a mole. We're going to go do the same thing with the ammonia, 1 liter times 0.15 molar, and we're going to get 0.15 mole. I'm still going to ignore the water. Now, this is not going to be an ice, so there's no X here, one arrow. So we're going to look at these values and figure out which one is the smallest. The smallest is the limiting reagent, and that is hydroxide. So we are going to subtract 0.1 from this side, subtract 0.1 as well from the ammonium. Because it's on the other side of the arrow, we're going to add 0.1 here, and final, we're going to have 0.25 mole of ammonium and 0.25 mole of ammonia. So at this stage, anytime you get to your F, the first thing you have to do now is reevaluate to figure out what you have. Do you have a weak acid, a strong acid, a weak base, or in this case, we have buffer. And we know we still have a buffer because we still have both the weak base and its conjugate acid. This is going to allow us to use the Henderson-Hasselbalch. So we know that our pH is equal to pKa plus the base 10 log of the concentration of the base over the acid. pH is equal to pKa. We already got pKa for the first part, which is 9.25, plus the base 10 log of the base. Now we have 0.25 moles of ammonia. In order to get concentration, we need to divide by the volume, 1 liter, over 0.25 moles of ammonium, NH4+, divided by its volume of 1 liter, and we can see what we have. Now notice, because we have this all in the same container, our volumes cancel, and in fact, on this part right here, you can just use the ratio of moles. Again, you can use the ratio of moles because the volumes are going to cancel. Notice also our moles are the same, so we have the base 10 log 1, which is equal to 0, and pH is equal to 9.25. Please note pH equal to pKa if you have equimolar amounts of the base and the conjugate acid. So let's do the same problem, except instead of adding a base, we're going to add an acid. We still have ammonia, ammonium, but now we have HCl, which is H plus, and Cl minus. Now we also have some Cl minus over here. We're going to ignore these because they are inert. We're going to see what we have. We have a strong acid, we have a weak base, and we have a weak acid. Now note the strong acid is going to react with the weak base. Why? Because acids react with bases. We know that this is a strong, so we are stuck with a mole chart. So our reaction is H plus NH3. It's going to go one arrow into NH4 plus. We're going to need a mole chart, and we're going to call this ICF. Our moles here are going to be 0.1 for the H plus. This is still going to be 1 liter times 0.15, and that's going to be 0.15. I'm just going back to the original amounts. This is 1 liter times 0.35 molar, and that is going to give me 0.5. We need to figure out which is our limiting reagent, and that's going to be the smallest, so we're going to subtract 1. On the other side of the arrow, we have to make sure we add 0.1, so that now we have 0, we have 0.05, and we have 0.45. This is still a buffer. Still a buffer because we still have both the weak and its conjugate, and so our pH is going to equal 9.25 plus the log of the base over the acid, which is going to equal 9.25 plus the log of the base, which is 0.05, over the acid, which is 0.45, and that's going to give us a pH equal to 8.30. We have added a strong acid. We, in fact, have added enough strong acid that if this were pure water, please note 0.1 moles in 1 liter. If this was pure water, our pH would drop to 1. But because this is a buffer, our pH has only gone from a little around 8.9 to now about 8.3. Buffers resist change in their pH. So let's make sure we can put this all together. So a student needs a buffer at 4.33. Which of these should she use? Well, we know that our buffers have an equation of pH is equal to pKa plus the log of the base over the acid. So the first thing we're going to need is that we are going to need a combination of a weak plus its conjugate, and then we're going to need pKa near the pH. Those are our two requirements. So first of all, HCl with NaCl. Well, this is not a buffer because this is not weak. Okay? NH3 with NH4 plus. Well, this is a buffer because this is a weak base and its conjugate acid. We've done this problem when we know pKa is 9.25. This system is basic, not acidic, and this is not going to work either. We need a pH of 4.55. Well, this is benzoic acid. If we look up benzoic acid, we are going to get that Ka for benzoic acid is 6.3 times 10 to the minus 5. On a test, you would be given that. Here, you're going to need to look it up. If you get pKa of this, pKa of this is equal to 4.20. Now, 4.20 is within 1 pH unit of what we need. Therefore, the buffer system that we need is going to be benzoic acid with sodium benzoate. So the question then is if we want 4.55 and our pKa is 4.20, what is the ratio here of the base over the acid? Well, we can do the math. We take 4.55 and we subtract 4.20. We're going to get the ratio that this has to be. This is going to be the log of the base over the acid. Well, we know to get rid of a log, we take 10 to both sides. 10 to the 3.35 is equal to 2.4. So 2.4 is equal to ratio of the base to the acid. So we're going to need a ratio of 2.41 for our base to our acid to make this work because the pH that we need is above the pH that we start with. So let's make sure that we understand our reaction. So we're looking at our blood buffer system, and we're looking at the combination of dihydrogen phosphate, which is H2PO4. Now that has a negative charge. The other part of our blood buffer system that has the phosphates is hydrogen phosphate with HPO4 2 minus. In order to see what happens when we add strong acid and strong base to the system, we have to identify them. The one with the more protons is our acid. The one with the fewer protons is the conjugate base. And what we are going to do is we're going to take and we're going to add H plus to this, and we're going to add OH minus to this. Now we know that when we do this, we are simply going to interconvert from our weak acid into this conjugate base and vice versa. So if we add a hydroxide, it is going to react with the acid. We're going to pull off a proton, and when we do that, we're going to make HPO4 2 minus plus water. The key when you do these is that if you add a strong acid and a base, you better take part of your blood buffer system or part of your blood buffer system and convert it into the other part, the acid into its conjugate base. If we add an H plus or an H3O plus, we know acids are going to react with bases, so it's going to react with HPO4 2 minus, don't lose your charges, and it's going to make H2PO4 minus. And here, again, it's a buffer. What do buffers do? They take and they neutralize added strong acid and base. How do they neutralize it? They take and convert it into a weak. So a strong base has been converted to a weak base, and here a strong acid has been converted into a weak acid. These are going to have a very small change in its pH, which allows it to resist change in its pH. Buffers.